we're going to talk a little bit about our equipment, and you'd say, well, how do we get started, and what's a good sort of system to go through? You can see on my left that we've got our starter and extension system for chemistry, for essential chemistry. What's nice is that it's got a full, I mean, it's built to support our chemistry curriculum. The book that it came from, I do have the textbook it's out there, is what it's supporting, and it will have links in the textbook, but it also has a much larger lab station, all of which, or I should say, the lab stations listed, 73 labs, are part of this much larger book. But when you get the starter and extension lab kit, you will get 10 of those, which we think is a great way to get started. If you've got just some good starter labs, I picked them out across that full set of labs. And what's nice is that I picked them so that they would be, spaced out throughout the semester, so that would feel like you have plenty to use, in a way throughout your year. But our essential chemistry starter lab station is what we're going to be going through, and the equipment that's there. And it was put together to support the chemistry curriculum, but it could support any. And the labs in there are very much what I'd used. I taught for 30 years, and they're very common. That's why I chose those. The equipment that you're going to see, it's going to have, I'll go through the middle sort of image first. There is that you can see we've got a pH sensor, a temperature sensor, a pressure sensor. Again, we're going to use those early on in terms of types of reactions and the way things bond, and how they dissolve, for instance, to tell a little bit of those properties of matter. On the bottom, you see things like the drop counter, so that you can deal with solution volume. It will also have a conductivity sensor once you get to solutions. The colorimeter is going to be a great way to do some spectrometry, which, of course, you may be teaching earlier in the year when you talk about the way light and matter interact with each other. It's got a condenser and a voltmeter. So we will take a look at all the ways that we can use those. It does come also with like a periodic table, some molecular cards that are on there that talk about properties of molecules, the spectra, and what to expect to see when you're looking at a spectra, what can be then sort of quizzing, or trends that are about each of the elements. So you can see trends in the periodic table that all are included with the write-ups that are in the experiment library for this. We'll go through that in more detail. What you see on the left is if you are opening up the Essential Chemistry Starter Lab Kit, you'll see the 10 labs that are included. Comes with the equipment that's all here, which I'll show you here in a second. But they come packed. The first thing you'll notice is that's going to be at the top. Inside the lab kit itself, you'll notice that there's the equipment that we'd previously shown, all packed into a Gratnelk for easy storage. Can be packed at the lab station so that students have access to each of those. I'm going to pull this over a little bit so you can see it better. Pull the lid off. So, as a matter of fact, I'll give you a top-down shot. So you can see it comes with a periodic table. That's the printed guide, which is upside down. Should be able to see that we've got, each of the probes that are coming inside, the package and accessories that are going to be for instance, pressure. You got some tubes and stopper, pressure sensor. But all of those activities are packed in a nice storage solution for you. And it's really quite a nice way to be able to manage all the equipment that's going on. It does help as soon as students are done, if they set up a few of the plugs for charging those, that keeps those charged throughout your day. All of the probes that come with batteries generally last about 6 to 12 months, depending on how much they're being used, and so don't need to be plugged in, but they're, like the voltage sensor has a USB charger that will plug that in. The labs that you're going to be doing, if you look across here, I know when I'm thinking about my chemistry year, I start off with elements and their names and naming compounds, but I quickly come into things like properties and whether something's got chemical change or a physical change. And so we've chosen a lab that would go through those, and I'll demonstrate each of these as we're taking a look. The specific heat of a substance comes generally pretty early in the year, and we'll take a look at what we can use temperature sensors to do that. How bonding will affect the properties of a substance, particularly as it goes into solution. Types of reactions so that they get chances to see what our general causes of reactions, but also ways that we can measure that. Evaporative limiting reactions, so that reagents, so that you can see when we get to stoichiometry and the math of chemistry that you'll using stoichiometry, but also in very visual ways, so that it reinforces the mathematics behind those that students work with in a very visual way. Evaporative cooling, so as you start to talk about gases and the intermolecular forces, they understand bonding and the way that molecules share electrons, that gases are going to start to be used to describe if they have weak intermolecular forces, they turn to gases easily, and we study how things evaporate and cool things off. You go to solution concentrations with spectrometer or colorimeter, onto pH, because that's a type of solution, and we can follow those. What is pH and how titrations work, and then finish it off with electrochemistry at the end of the year. So it really is a great overview of what you might cover in your year, and that can work as a suggestion. And if you want to look for others, you'll find that you can look online, which I'll go through at the end, so you can see where that all is. And you say, okay, I can find these. For instance, if I use this and I make a photocopy and I lose it, and I cut it out of my book, it's got some pages here. Each one starts off with the title, and then works its way down with the equipment that you're going to need, the procedures, and has it filled. And let's say, hey, I lost this from one year to the next. You just go on and look up the chemistry, essential chemistry starter, and you will get to where you can find that set of handouts again, that you can print it from a fresh new copy right away if that's what you want to do. But you can keep this right at your desk as well if you are one that likes to keep that physical kind of component there. And like I said, after I've gone through the labs, I'll go through actually to the website again, just as a reminder of how you can find those, and that you can know that you can see all the things I've talked about. All right, I'm going to put this off to the side. Excited to get started. And like we said, the first lab that we'll talk about are just differences between physical or chemical changes. And let me pull this out and switch over to a long shot here for us. There we go. We get a couple of ingredients. In general, I've shown you the equipment shot that comes with each of those, and I'm pulling back the curtain a little bit. Students don't necessarily need to know that each of these, they could be in just marked A, B, C, D kind of containers, so that they can look and see what sort of the properties are. We'll use a beaker to peek at some of the materials as we make mixes of those. But the substances that we're going to use are just food coloring from blue. Put those in that order: blue food coloring, yellow food coloring, and then we'll have a dilute solution of hydrochloric acid and sodium hydroxide. And so, let me make sure I get the sodium hydroxide. There we go. Always look twice. Now, the first thing that we're going to want to do is just take a look at what some of the readings are. And I'm going to show you how that connection looks. And then I'm going to drop back, instead of having to go through all of the instruments and getting them on there. I do have a screenshot of what they'll end up looking like as a group, because we do have a starter kind of place for that. Here is what our program is that we would use, SPARKvue. SPARKvue is going to be able to connect wirelessly to any of our instruments. The instrument, like I said, that we want to take a peek at today is, let me grab one of those from here. This first one. Got a pH sensor. I'm going to choose a conductivity sensor. Okay. I'll go ahead. I'm going to turn those on with the power button that's on here. Let me grab this one. This is from the kit. The other one was mine. Put that in here, and I'll go ahead and put the pH sensor in there as well. So the easy and first start is to get your probes sort of prepared. Students will learn that they can turn it on with the power button that's on the device itself. Okay, I'm going to hook up to these probes to the computer, so you're watching me as we're doing this. The Wi-Fi devices will be displayed up top. I can see there's my conductivity pH. If I have a room full of these, let's say I have 20 students that are all hooking up their pH sensor, you'll see a big long list of those, but the one that's closest to the computer, the Bluetooth strength itself, will be the one that's highest in the list. So that helps to make it easy. If another student steals this and says, oh, I took that one, or it disappears off this list and the student can't find it, they just turn off the sensor and turn it back on again, and it'll come back into the list. It'll unpair from the other computer. So we're going to turn that on. Actually, so that's the connection process, that you just click on them and they go up into the connected list. But that is the general process. I'm going to cancel this and actually start from this lab, so you can see that we're going to open a saved lab. The saved lab is, hey, I've got a textbook that's got these in here, and when I hit my open saved experiments, not saved, sorry, PASCO experiments, there we are. I can go into the essential chemistry list. Here's all of those from that essential chemistry, all 73 labs, and including the 10 that come with the kit here. Now, what we're looking for is the physical or chemical change. That's the second one that's right in here. Okay, it will also be printed on the top of that handout so that we can click there and go start. And why I say that is because what's nice is all of those sensors that are turned on, the ones that are coming with this, will show up on here, pH, sensitivity, and temperature. I can turn on one of the temperature gauges and make sure that's hooked up too. Go. And what I want to do is make sure I'm hooked up, because I use this. We saw how I hook them up in general. If I'm at a general purpose and I didn't use a starter sort of quick start lab, but now I can hook up the conductivity, make sure that it's reading from this particular conductivity and the temperature sensor. Okay. Okay, now I get the temperature and conductivity. Okay, there we go. I can see at the bottom the live reads of those, so that it's not necessarily showing up in this until I start collecting data. I'll go ahead and hit the start button so that we can see what the temperature and the conductivity and the pH are. I'm going to start off with one of my solutions. In this case, I think this is C, but I'll add the HCl to sodium hydroxide. The other ones, the students will see they don't change a lot. We're going to watch this reaction. Okay, we'll start that again. Okay, so we see the temperature is about room temperature. The conductivity is, make sure I'm connected. Okay, and I'm going to go ahead and mix my sodium hydroxide in with that. Now we'll go ahead and give that a good stir. Oh, yeah, I see my conductivity is not connected. Well, I'm going to do this and switch over to my other conductivity sensor. Maybe low on battery, so let's connect that guy. And we will reconnect, start that again. Conductivity, there we go. Start those over. And yes, that's much more appropriate. We have very conductive, in other words, a substance, as we're talking about chemical and physical change, that was 14,000. And it was pretty high to start with just the acid as well. We've got a little change in temperature. pH is still quite low from the acid that's there, and I could add more of these, but that's the connecting process and the gathering. So what I want to do is say, okay, let's switch over and take a look at what a standard sort of beginning set of properties for each of these solutions would be if I was pouring those in. Solutions A and B are two of the food colored solutions. What you notice is, yeah, they're all about the same temperature. Okay, the conductivity, in A is very low. It's just organic compound, doesn't dissolve into ions. Okay, and it's about normal water pH. I could ask the question, which of these is the other colored water? And you'd say, okay, what do I need to know? It's an organic compound. It's not something that's ionic. And so we would just look to see, is there something similar to this one? Yeah, this is the other substance that's colored. Okay, it doesn't have much conductivity. pH is pretty normal. What's left? You got some pretty high pH and a fairly low pH. Sorry, low pH and a high pH. Pointed here. So when we mix those, A and B, we should see the combination comes out to be fairly non-conductive. Okay, and the other combination comes out still to be pretty conductive, but a little bit acidic. So our base acid is showing that it's changing as it's been added. Each of those then can be reason to say, oh, when I add something to these, I don't get much change in conductivity because they don't do anything. But these two are joining to make things less conductive from when they were very high, 13,000, and down to some lower, or 19,000, 20,000. And like we see on the bottom here, it comes down to 5,000. When those two neutralize each other, they go from being ionic substances. HCl is a good ionic substance from left and right side of the periodic table. Sodium hydroxide, polyatomic ion, that dissolves very well. So depending on how much you get into the solution, if you added exactly the same amount, you can neutralize it all. But that's what the students are there to look at. Yeah, I poured eyeball sort of amount, so on the live screen, they may not show as accurately as what we see in the data set there. But that's the idea. We want the students, we saw how easy it was to sort of hook up this sensors and to quickly get some data. And that's where they're going to start to understand the differences between chemical changes or just mixing two substances that don't have any kind of reaction. Okay, let me rinse these off and we'll go on to next. Setup. Awesome. Okay. Next is specific heat. And I like these, in terms of even just the thinking of how these labs were set up. But what I have is I've got just some ice here. Let me switch to an overhead sort of view. I've got some ice here, and I've got then a piece of metal that's been sitting on ice. We know what the temperature of that is. It's got water in there as well, so it's really ice water. Make sure it's got plenty of water so that it's not warmer than, or colder than the surface. But when ice and water are together and they're sitting in equilibrium, they're going to be 0 degrees. The next one is I took some hot coffee water from our machines, because that's a nice quick source, or if you got a hot pot or you're just heating things up on a beaker. We start with the hot water in one side, so that's going to be the stationary amount. What we're going to do is we're going to add the metal piece here into that hot water and to kind of follow that temperature. Let me grab one of my temperature sensors here. I've marked down that you start off with even amounts, hot, cold water. As a matter of fact, that's where I was going to start from here. There's 2 sets. I'm going to add the metal second. Let's add 2 amounts of water. And I stuck to a measured amount, 66 grams. So I'm going to let those 2 mix for just a second to get them up to cold temperature, and I can use my temperature sensor to do that. But again, every time I'm going to show you the temperatures on this, and I have worked it through so that sometimes I'm just going to do a walkthrough. Other times I'll pull up from the lab itself. I'll go ahead and start a new version of our program. And let's start a new version of SPARKvue. Okay. If I'm just starting, and the only thing I'm using is temperature sensor, so I'll go ahead and start, just so you see, here's the standard sort of start. If I wanted to open the specific lab that's with this, or that comes with it, I can choose to open those. I'm going to choose a temperature sensor. Again, I've got now 2 to show you what it looks like as it's, as others are on. I'm going to choose the 971. And again, as I get closer, the other one's actually right next to my computer, so that's why it shows up. Double check. Yep, that's the one I want. We're going to go ahead and just start with a graph. Now, to be convincing, I'm going to watch what happens to this water when I start it. Make sure I'm connected. So 1, 3, 4. Mm-hmm. Okay, so we're down here by 0 degrees, and it's getting a little cooler as I start. I just wanted to show that's where we're starting up. Okay, that's convincingly close to 0. We're going to measure. I have 60 mils of warmer water. Now let's go into this water so you can see what that starts out at. I'll hit the start again. Our second run, what's nice is you'll see that these, drop the last reading off, and it's warmer. And this is in Celsius. So this is going to go up maybe 25 degrees. While that's going, I'm going to measure out 60 mils of this cold water, which I'm assuming is 0, so that they're just about equal amounts. The reason I chose 66 is because I wanted them all to be equal, the warm and cold water and the metal that I put in here in just a little bit as a comparison. I'm going to keep that nice and cold. So my guess is for you, we're starting off with 0 degree water. It's a little warmer as I hold it here, so I'm going to try to pour this quickly. It's come to about 28 degrees. If I mix these two, go ahead and make a guess at what these two are going to come together as. 2 sources of water, equal amounts of mass, and we're going to pour those together. Hopefully you've got a guess in mind. Let's pour this and see if it comes out. I certainly have an idea what this may come out to be. Okay, we're close to 28. The other one was close to 0. Ideally, we should come down somewhere just below, close to right between the two. And the only thing that may have caused some change that's a little warmer is because I had it in this glass, which may have been a little bit warmer. I'm coming into 16, so it's pretty close to halfway. And the bigger that you choose, if you can get nice warm water to start with, like 35 degrees or something, and then you pour the ice water in, that you'll get more convincingly to about that halfway point. Okay. So students can start to say, okay, equal amounts of hot, equal amounts of cold should come down right in between. Now, what I'd like to do is we're going to open up our second glass hot water. Again, I took about 66 mils or in this. Let's go ahead and I'm going to start our third run. Put that in there. Hopefully it'll go back up to about 28 because they both were from the same warm source when I started and gathered those. Okay, and now instead of pouring in an equal amount of water, what I'm going to do is I'm going to put an equal amount of this copper in here. So what we saw before is that the same warm and cold water, the same amount went to an exact in between. Should this go with metal? Should it go to a warmer condition when I put equal masses of the two, or should it go below? And that's the driving question I want my students to do. So you're seeing me doing this sort of as a demo, which certainly this equipment is exactly that. You can do it as a demo, or you can get your students as you print off the lab, and they could be running those. I'm going to go ahead and move this now. We're assuming this is 0 because it's been sitting in that ice water. We're going to put that in here, and I'm going to stir it a little bit, and we're going to see what happens. So we're going to see which was substance, same amount in both cases, holds more heat. And so I think pretty quickly we can see, okay, we had a cold metal going into this room temperature water, and the metal had far less influence. It doesn't have the heat, the capacity to heat that water does. Now, if I was doing these with, the labs that are both on the front side and back side in the larger text, we'll get into more of those calculations. But I just want you to get an idea of what we're doing, even as a class demo, that students can get a feel for the capacity that capacity of that metal to lower this temperature was nowhere near what water's capacity was, even though they used the same amount of mass of those two substances. Okay. Go ahead and move that off to the side. This one off to the side. Okay, I'll go ahead and quit just so that, again, you get used to seeing how we start and run each of these. So that was specific heat. Um, and whatever whatever block of metal you use, whatever that mass is what I was ending up using as the warm and the cold waters, just so they're all the same mass. And that concept then becomes very strong, deposited in students' minds from evidence, and then they can do the calculations. If everything's varying, they don't see the patterns as quickly, and that's really kind of nice. Okay, types of reactions. Ideally, what we've seen in that first example was that there are two kinds of substances. Substances that when they go into solution, they're really conductive. Okay, thank you. So in the first example, we saw that we have two types of substances. When they go into solution, they split apart and they're really conductive. As a matter of fact, one had pretty high pH, one had low pH. But in general, they're conductive. The other ones were not that conductive, even when you mix them or when you put, the really conductive acid into one and the really conductive base in the other. So that is a start of understanding sort of a fundamental difference between two types of matter. Now, what we're going to do is types of reactions that you can see here on the left are all good examples of the types of reactions that students are going to have to learn. Double replacement reactions, like in this first one, you have two-part compounds. Others are single replacement reactions, like number 3, putting something like magnesium into hydrochloric acid. We've got things that are single replacement, like number 6, that zinc and copper will continue to sort of, compete against. I'm going to look at one with some measurements, like we just did, and I'm going to just take a look at our hydrogen chloride and my sodium carbonate. Reaction number 4, just so you can see what that process looks like. I won't go through all of these, but all of those are great, and using evidence to sort of follow to see if there's hints of reactions. Does it gain a little bit of heat? Does it gain a lot of heat? So we're going to go ahead and I'm going to get out a beaker. Again, I'm going to choose my baking soda solution, which I believe is, here we go. Here's our baking soda solution. And I'm going to take HCl. Okay, and we've got our 3 sensors that can measure these solutions. We've got my temperature sensor, I've got a conductivity sensor, and I've got a pH sensor, just to see what happens as we add those in, to see if there's some changes that are occurring, as that reaction happens. So first thing I'm going to do, if I'm looking at this fourth step, HCl and sodium carbonate, is let's go ahead and I'm going to put the sodium carbonate in here first. We'll get a feeling for that temperature. I'm going to let it sort of sit so that they get in equilibrium, and then I'm going to pull up the program. All right, I'm going to put in 50 mils roughly here. Yep. So I've got my 50 mils. Sort of as a demo, it's easier to see that way. And then I'm going to start up my software. I'm going to show you the other way, pulling up a program. Again, I'm doing these so that you see both. How do you start off from just, hey, I'm going to use this as a lab tool, or I'm going to start up with a experiment. And so I'm going to go over here to the experiment. Okay. Last time I went to just a sensor. But again, I'm going to just keep reinforcing these ideas. I'm going to go into essential chemistry. That's where all the 10 labs that come with the starter and extension lab kit go. And we are looking, here you can see, types of reactions. Okay, so we're going to look down till we find types of reactions. If you had the printout, it would have the number there. Let's see. Types of reactions. There it is, 7B. All right. So go ahead and let that open. Here, we've got our 3 instruments already set up so that the student wouldn't have to. We're going to make sure we're hooked up. We'll make sure they're all turned on. I'm looking for a little red blinking light. pH sensor, conductivity sensor, temperature sensor. Okay. Go to an we can go to an overhead shot. or yeah, that's even better. A sort of side shot so we can see kind of what's going on. Now let's say, look up to our pH. And they'll hook up picture, conductivity. There we go. Nope. Nope. To make sure they're on, I didn't get that to go in. There we go. Nope. I don't want to update that right now. Okay. Let's make sure that they all hooked up. Thinking. It's nice on these sensors. They just have a back sort of screw for nickel batteries on the back to change those out. I'm looking through. I see all of those are hooked up. They're all in the, on the top of this list. And let's give that a go to see if they register. There we go. Start that again. In a second. Each of these reactions are going to be driving energy to go through, so that might change the temperature. The number of ions might change, that we'll see in conductivity, and whether its substance goes from being basic or acidic to see if that change occurs. Okay. I'm just going to go on the, yeah, I'm going to go ahead and we're going to start that again. Now, I've always loved these to start the beginning of a question. You say, well, how do I grade these when students, can hand this in? But I'd start with a question that the students could ask and then have them sort of gather data based to answer their own questions. And there might be just a quick warm up to see if they can't. Hey, is this substance changing in conductivity when we mix them? Is this substance changing in, the amount of acid or something? And they can answer those questions. And that's what I grade them on in terms of, oh, yeah, didn't want to do that, did I? Let me go back there again. I like the big digits readout when we're doing the demos. Let's go ahead and get that again. 7. There we go. Okay, so we got high conductivity. We got a little bit basic, 8 and 22 degrees. So I'm going to add another 50 equal amounts of this, and we'll just watch kind of what goes on. Get it right up there to about 100. I can look closely at the reaction. Ooh, I see lots of bubbles. That should also be something students by now, in this point in time of the year, are used to seeing. If I stir this, I can actually release some of those. I've got some more bubbles in the bottom, particularly of the carbonate with the acid. That we see the pH is swung, from this kind of 8 side down to 7-ish. We're losing a little conductivity. Okay, and students make those kinds of observations that there's a reaction that's going on. Ideally, when they have finished, they've seen this and they've then listed out the full reaction as part of the handout. And they'll put evidence down here of how much the pH changed, how much the conductivity changed, of which they can see all of what's going on there. So, okay. All right. In each of these, as students kind of get used to this, of what they're going to be looking for is listed. All the materials that are on here you can see as well in teachers material, which when I get to the end I'll talk about teacher materials. The next one, reaction wise, that I want to talk about, let me rinse these off. Okay, put these guys over here that I'm done with. So once I've finished typically in the year with the types of reactions, then we get into understanding moles, the fundamental sort of numbering of amounts of chemistry, and how to talk about reactions. And this would be maybe a little early, maybe right around now, maybe on moles. Uh, it depends on if it's my advanced chemistry might be well through this and dealing more with problems, AP sort of problems, but that we want to see what limiting reactants would look like. What's nice about this is that we have a real good comparison. I'm talking about a reaction between baking soda and citric acid. And I didn't put any numbers on here. You may notice this is not balanced because we want to determine what that is, what those coefficients are experimentally. Okay. And this one I'm mostly going to just show you as a demo again, so that we don't go through every one of the 10, but that we see, the ideas. What's great in this one is that you can use the baking soda and vinegar instead of citric acid. And you can just put various amounts, measure out 1/10 of a mole of baking soda, or so that they give these ratios. In other words, 5 times the amount of baking soda, which is in the bottom. No, the baking soda is in the top as a powder, and the acids are in the bottle. But you can see at 5-to-1, you don't quite get the reaction ratio that you need. When you have twice as much and one of the other, that you get a little more than you had before. And as you get to an ideal ratio, you see, I can make a certain amount, but just changing that ratio by now giving more of the one of the reactants, that you don't really create more of your products. Something in here is, by increasing it, is creating more of your product. But after which you reach a point at which no more added is going to create more product. And that is our idea of our limiting reagent. And get the students to sort of take a peek at this. This is part of in our PASCO portal, in the videos that support, what reactions you might be wanting to do in chemistry that you could use to see as an example, and we pull these numbers out. Now, this citric acid has a different number of coefficients. We're talking about baking soda here and citric acid. And so to discover what those are, you're going to be marking out 5 runs, adding slowly increasing amounts of citric acid into this baking soda solution. So you start off with a little bit of the citric acid, you add more citric acid, and you mark down how much is gathered. Okay, in terms of pressure, you're using a pressure sort of system where we put the pressure sensor into the vial itself, and then you measure what's the pressure that goes on. It's a little slower reaction as well, and which is nice, so that you don't pop the top off. Okay. Yep. Oh, camera. Thank you. So inside of the kit itself, you're going to have the pressure sensor. You're going to put this on top of a large Erlenmeyer or a collection bottle, and then hook it up with a tube that will allow that to be gathered in pressure, and then you slowly increase the amounts of citric acid until you don't create any more volume. So and you measure that in terms of pressure because it's a closed system. So in other words, you get more and more pressure as these reactions go until this finally levels out. So then the question is, and each of these amounts is equal molar, double the amount, triple the amount of the baking soda, 4 times the amount of baking soda, and 5 times. Again, try to use in all of these labs something that's very whole number oriented. You can certainly get on to then, the problems that they have to solve can be tenths and, all sorts of decimal places. But in terms of the labs that they get the ideas, we want to see it's a 1-to-1, a 2-to-1, a 3-to-1, a 4-to-1, a 5-to-1, that they can say, somewhere around here, maybe a little higher, maybe a little lower, seems to be a very similar amount as your end product. We've limited how much you can create because now that the baking soda solution is limiting the reaction. That's a great one to use pressure inside of a closed flask to be able to determine. As we finish those, typically I go off into like gases and then liquids and solids and the types of bonding and the intermolecular sort of attractions that are going on. So we might be able to take a look at the differences between certain substances, and I've got equal number of moles, and they're not equal mass, but we took 0.05 moles of each of these substances: baking soda, sugar, salt, and vinegar, um, to determine sort of what happens to them as we add water. Okay. And see as it dissolves, can we check the kind of bonding that might be there? Does it break into parts, especially if they're ions and ionic and be conductive? And does it break into the same number of parts, which we'll be able to measure with the conductivity? Um, so we'll take a look. And as a matter of fact, let me get some water here. We're just going to start from one end and work our way down to the other. So the first substance that I'm taking a look at, let's go with the order that I have on the screen. Okay, I got salt in here, and I'm going to add 50 mils, actually 100 mils. Let's make sure we get all connected. I'm going to add 100 mils to each of these to sort of watch what happens to conductivity. So turn that on. Let me go ahead and start our software. Okay. We're just going to follow the conductivity. Choose a graph. Okay, I see that it's my conductivity is over here on the side of this graph. That's what we want to watch what happens over time. Okay, right now there's no conductivity because there's no water. There's nothing that can move these substances from one side to the other. I'll go ahead and start. You should have nothing. That looks great. And I'm just going to measure it out to 100 mils. And I'm going to use the device to do a little stir here just to make sure. Okay. Of course, we know the salt dissolves very well in water. And students can do this, and it'll take maybe a minute to get that all to dissolve. Give that a rest, and then one more stir. Okay, so we've reached as high as that thing is going to go. All right, I'm going to go ahead and rinse this off, and now we're going to compare that to our baking soda. And again, it's mostly qualitative. I mean, yes, these are quantitative numbers, but we want to get the students to have a really qualitative sort of understanding of what's going on. Here's another substance. It's very conductive. We'll give that just a little bit of stir. We should see that we can get these conductivity sensor. I'd say is really good at up to about 40,000, which is just under C sort of salinities. But after 40,000, it's probably not as linear. Maybe 50,000 is the max that it comes off as, but that's baking soda. And if anything, I'd say it's probably not as conductive as salt, which is probably true. But that's equal amounts. Okay, let's continue this next one down to sugar. Oh, let's rinse that off though. I'm going to go ahead and add 100 mils of water to this. Back down to 0 again. There we go. Oh, maybe that needs more stirring. No, I know, that doesn't need it. Of course, organic compounds like dissolves like, especially when we get to solutions. And here's a great case where it doesn't need to necessarily be ions that the substance breaks into and lets water surround each ion, which becomes highly conductive. But if it's just got a molecule with OH, water has OH, it likes other molecules with OH, but it doesn't break apart or dissociate. And so sugar is a great example. So I've got vinegar. Vinegar actually is acetic acid, which is an organic compound. And so what would we guess? Should it go as high? Should it go more than sugar? Should it go as high as salt or somewhere in between? And what's nice here is that I'll go ahead and rinse this off while you're thinking about what amount that should be. Okay. Vinegar is known as a weak acid, so it doesn't break apart probably as much. So maybe less than salt. This is 5% as well. And all of these I wanted to make a 5% solution. So I measured out 0.05 moles in 100 mils. And yeah, so while it's 5% and does have as much salt, or sorry, ions as the previous two, it only 10% generally breaks apart. So it doesn't all break apart. Here's a good start to understanding maybe a precursor to acids and bases. It is salty. It does conduct some, but it isn't as good as the starting two. Uh, and so they then start to get exposed, students will, to partial dissolving or partial ionization. Obviously, the vinegar is all dissolved in this case, but it still hasn't broken into its H into solution, and acetate over here able to conduct electricity. But what a fantastic way to sort of be exposed to it and maybe have some questions. Ask, why isn't it as conductive, even though we tried to make the same amounts in all of those? And that's what we'll leave for, the next chapter when we get to acids and bases, which is a great way to sort of go. Okay. There we are. Now, I want to go to evaporative cooling. As gases, especially as you start to talk about intermolecular attractions, they may have brought that up from the very beginning of the year, and what's a polar bond, what's a non-polar bond, but how does that affect properties as you transition from gases, as you go liquid solids and get into then solutions? That's a nice lab that we can grab here. You really could do a couple of things. This one is looking at the difference between hydrogen bonding, so that might be like acetone, um, alcohol, and then water. Acetone has no hydrogen on oxygen, so no hydrogen bonding. Um, Ethanol or alcohol that has one hydrogen bond, and the water got two hydrogen bonds. That's a good example. If students are sharp and you're looking at maybe you're enriched or your AP chemistry, you can look at even just the size of the molecule as well. One carbon alcohol, a two carbon, like methanol, ethanol, and propanol. But I'm going to stick with the hydrogen bond because that is the strongest of all those. I'm going to go ahead and open these up. Actually, I don't have anything in this container because the plastic would start to go out and melt. So I put that in a little glass test tube. And the next one is the alcohol, and this third one is water. Now, what's really nice about this is if I get three of my temperature sensors and I want to compare these, I'm going to go ahead and turn all three of those on. We're going to use one for each. I want to get a drop on the end. And the biggest key when I'm doing this is you don't shake it off. You want that drop to hang on the end. So I just lift them up and continue to hold that drop there. So while that's started, I want to make sure all my temperature sensors are on. I want to go ahead again and start SPARKvue. And we're going to look for evidence that it's easier to escape. When those molecules escape, what happens is they're the fastest vibrating ones. They're the ones that have the higher kinetic energy, and that's bringing the temperature up. As they escape, the pile that's left behind is cooler or slower. And so we want to see which one is like that. Less attraction between molecules ends up evaporating faster and cooling off. So let's go ahead. I'm just going to start. Notice I'm switching off. Sometimes I go and I grab the lab-based description. Otherwise, you can see you can make your labs by just connecting to each of these sensors. I'm doing that purposely so you feel comfortable that says, oh, I can do this. As department chair for 10 years, I worked with my teachers to really just practice this. And the best way is just to play. The temperature sensors are a great example. Take them out, and just turn them on and play. I must have had some data on. There we go. Delete the data. Thank you. And just play. And so that's the best way in the world to get used to these. You say, I'm not so comfortable or whatever with these because it's the first time I've gotten them, or I've gotten them, but I've not used these specific probes. Man, just get in there, turn them on, and play. I'm going to put them in increasing number of the last three digits so that I know the one hydrogen bond has the lowest, so zero hydrogen bonds has the lowest number. So that's 140. The next one, 384, that's got one hydrogen bond, and then 985 has got the least. Okay. Now, the other thing is that I don't want one. Let's put these all in one graph. You can see me manipulate the graphs just a little bit here. Let's go to X this guy out, X this guy out. I'm going to add 3 so that they can be compared right next to each other. Okay, now I'm going to choose that first one is going to be the one with the lowest number, the 140. Notice how I'm getting the data to go on here. I'm just choosing it in the pull down menus. The next one is 384. That's the alcohol. And then the water is 985. That's got 2 hydrogen bonds. Okay, awesome. I look on here, 22 and a half, 23. Yeah, they're all pretty darn close. All I'm going to do is just lift these up, and let's watch what happens to the temperature as they start evaporating. So what's cool is we have sort of a difference in temperature, and you notice how some of these are sliding because they're filling the screen. If I go ahead and wait till they finish, I'm going to do a little trick here. Okay, we've pretty much evaporated this last one. Now I want them all to be in the same scale. There we go. And then I want to see them all. Notice all my tools down here in a graph are just showing. This is really nice. So we've got, even though they start at different, this definitely has a distinctly faster evaporation rate. That's this Y1. That's the one that has the acetone. It has no hydrogen bonding. Here's the ethanol. Okay, it's the second one we said in the order that we connected. And then the third one has water. It's water, and it's got a lot of stickiness, so it doesn't escape and bring it with it its heat. Awesome, quick example. Students can see this. As a matter of fact, if you got AP group, you can choose different kinds. Hey, let's see what the difference between water and peroxide are or something, and see if they can't argue their way through describing intermolecular forces. I'm going to go ahead and turn those off again. Okay. So as we see, we're all the way through to, gases. We've done some solutions. We saw a great acid examples and bases mixing. Put the caps on these. And what I want to do is just show you what the last 2 are. I'm going to, because I want to respect your time, we're coming up to the end of that, end of the hour. So let's continue on. Okay. The other labs that are in here, you would be able to take and put into our colorimeter. And you'll see as they absorb more color, you can choose 3 of these solutions that you know what the concentration is and put one in to determine its unknown amount. The 9th lab that's in this group is going to be starting from one acid, and you're going to dilute it, in a systematic way, and you're going to watch what happens to its pH and graph those sort of out. Okay, the students get an idea of the dilution, and the number of the hydrogen ions is changing as you dilute those. Titrations are really nice in the sense that you can see some quick graphs to not be so worried as students typically do, as they're worried that you're going to overshoot an endpoint. But when you're gathering that individual data, as a matter of fact, that is so convincing. I am going to do that one. Let's take that because I've got it all set up. I'm going to use the drop counter. The drop counter lab is a auxiliary lab that you can use. Here we go. So what I've got in here is our hydrogen chloride, HCl. I'm going to go ahead and put this down and into the earth. I'll turn on the drop counter. I'm going to go ahead and start SPARKvue. Okay, so I'm going to have pH sensor. Let's make sure that's turned on. Okay, drop counter. We'll make sure that's turned on. I'll hook up to the sensor data to see that process one more time. Okay, I'm going to hook to the drop counter, the pH sensor. We'll go to the graph. All right, I only want one graph, so we're going to have by volume, but volume is typically on this axis when we're graphing these. So I'm going to put fluid volume down here, and I'm going to show pH change as this fluid is added. What's really nice is just how fast you can do a titration, and students don't have to be worried about overshooting an endpoint. So let's see, we'll put pH on there, fluid volume. Okay. First thing I'm going to do is turn this guy on to let that start to flow. Oopsie. Oh, that's right. We'll deal with that later. And I am going to let the drops come through here, but I'm going to start this first. Okay, so you see there's no data coming across in the graph because there's no drops going through, no volume is being added. And then once it starts to drop, I'll just stir it like this. So let's watch what that does on a standard titration. Just want to get it to drip through. Go. Turn it this way where my hand could get into it. Let me turn this. Okay, that's doing pretty fast. This can count up to 40 drops a second, which is impressive. I'm going to do it more like that, which is maybe 10 drops a second. And we're going to watch this sort of change. You can put a stirrer in there, and we're going to watch that change go on. We've got HCl in the bottom, and we're dripping sodium hydroxide. It's going fast because the HCl's decently strong, so I wanted to get to the midpoint and see what this looks like. You can see it's starting to go up. HCl is being neutralized. And again, the speed at which this can be done is great, so that students start to realize the shapes of these are important. You teach with shape, and it can get beyond mathematics, but that idea of the shape is going to bring their understanding of mathematics along. A lot of students are, they're afraid of some of these numbers, and I love that these graphs kind of come out fast, that they can really make a difference by saying, hey, I understand what's going on. Now let's get into the math. We're going to try to look for the place where the pH changes quite quickly at the end when all of the acid is gone. Looks like it's changing pretty quickly. So we're getting to the place where we had 20 mils of acid, and I'm at almost 28 mils of base. Ideally, they should, if I mix these solutions exactly the same, they should have been as much as what I started with. But it was a little off, and that's due to my not mixing the two solutions the same. And now it's going to say, oh yeah, all the acid's gone, and it's just going to then go to the strength of the base. Okay, what a great and quick way to see sort of those relationships. There are a few tricks about finding this middle point. Some you can use your graphs here. One that I like to use is that this goes through an inflection. In other words, it's curved this way, and then it goes curved that way. So if I put a line through this, I can get where the line crosses is actually very close to the middle. So I'm going to use a selection and just do this super quick. Then we'll get on to finishing. If I put my best fit line through that area, you're going to see somewhere in the middle that it crosses. And again, you could stretch this higher or stretch this lower. But somewhere right around here where this crosses, where that inflection point is around 7.5. That makes sense. That's the volume, which in this case is 30. If those were equal strength, they should have happened as much volume as I started. Should be the amount that it requires sodium hydroxide to neutralize this, but I can use the MV formula and find out what the strength of that original solution was. Boy, it's just quick. I love it. And students really do get an understanding first, and then the math comes second. Okay. Let's go ahead and finish up. Lemon battery is fantastic, and really you can use any citrus fruit or, other things, pickles, whatever. And you're just going to put in metal strips and measure the voltage. Some of the challenges that's nice is they can see after finding which each combination, hey, how is copper compared to zinc? Just like the periodic table has in the upper right, much more elements that are good at grabbing electrons, and things that are lower don't grab electrons. So they create a voltage between them when you hook those metals up. Okay, so if they're closer to this direction, they're going to be better at stealing or pulling on electrons, and they create a voltage. So students are then going to use 4 of the strips to then find out which one has the biggest jump between those, and they can then have a contest to say, can you make the battery with the most voltage? Even better is putting two lemons together and see if they can figure out some concepts about, putting things in series or parallel. And it's just, it prepares them because they get experiences, and they can deal with that when they get to physics then the following year, which is usually the order in which that shows up. I've mentioned these 10 are just the 10 that come packed with it. So the whole kit comes packed with all of those instruments. Those are the labs that you're doing. It's good spread across the year, and that's fantastic. If you want even more to look for, then it's part of the Essential Chemistry Lab Manual. And you can get all those for free on our website, as a matter of fact. But let me go back one. Just look up Essential Chemistry, and Barbara put a link in the chat, so you can use that to get to those, and just pick the labs you like and then do those. But the 10 that come packed, printed, and ready for you on here are there, and then you can always go back and find either the 10 lessons that come with this lab collection, the Essential Chemistry Starter and Extension, or you can go to the full 70 that are in here. Now, you may say, I'd love that, but it requires software. Software's got some cost to it. What I'm going to suggest is consider this. We are just coming out with a sort of way to deliver all of our goods electronically. It's called the Portal. And Portal has one cost. As a matter of fact, the cost of it is less than the software is for your school to get a site license. And so while you have the Portal, you would have access to all our software, all the curriculum. It's really nicely organized. You would just go to one site. If you go to PASCO.com, you'll see it's on the top, it'll advertise the Portal, but it's something you can consider as a school, and then every class can get into it. You can set it up so that you use your school's one login, your one single sign-on, or they can, log in with your email, for instance. And then what you do once you get inside is say, oh, I want to go to the essential science that we just, we're talking about this whole hour. What's nice is that when you get in there, the videos that demonstrate how to use all 10 of these labs we have videos that you could go through and you can check out and watch. And, we highlight what's important on these. Okay. So if you want to get just-in-time training, go to the site, see the Essential Science. Now, it's also on our webpage that you can get many of these, but things like the Word doc, if you want to edit them, are available on the Portal where they aren't on the website. Things like, trying to think, well, here's sort of a quick summary. Again, it's $200 for the access to the Portal. All the core curriculum's there. You're going to get extra professional development. Hey, I'm using this pH sensor and there's something going on. It'll have a quick link to the help, or you can talk to somebody live online. So all that support is going to be there. And then all the software that we offer is going to be available for as many, classes and students. So consider that. That's another way that you can access our material. But if you just get the kit itself, all of the materials you need are going to be there. The labs that are printed, the equipment that's there, you'll need to supply all the consumables. That's not part of what we are selling, but that's what you would normally set up in your lab anyway. Okay. With that, if you have more questions about being able to get this, you can contact our regional PASCO rep. I will mention again, tomorrow, 24 hours or so from now, we're going to send you a link, and that'll give you a link to the video. It will also give you a short quiz that if you want to take, and you can get a certificate that you can put in your file if you need those. We'd love to have you to go there. So pasco.com/support will list who's in your area that can, be a local salesperson that can answer questions. You can also contact myself, R. Palmer at pasco.com, or Barbara B. Puglisi at pasco.com. Barbara's been working the questions that we have had on the side. So unless there were specific questions you weren't able to answer, Barbara, was there something that I can maybe answer before we turn off the recording? Okay. Well, with that, that really is our program for you today. It was a little longer than an hour and 5 minutes. But to see all those labs and how you can set those up, this is, what we do. And I think that the organization, the order in which those labs occur to build concepts is really strong. And that you would have a really great lab program that's adding measurement, that's adding, evidence-based sort of teaching for chemistry. And so with that, we wish you a great day and good teaching with great equipment. as you consider us and have questions, then just keep in touch.